So then I get started. I can first start with introducing myself. My name is Johan Windahl. I have been working at Modelon since in the beginning of 2007, so it's a little bit more than 6 years now. My background is that I have a Master of Science in Engineering Physics. And yeah, you see my email if you have any questions later or so. And also the phone number. Okay, so I get started with the library presentation. So here is the agenda for this presentation. So I will start with the so I will start with discussing, take a look at what is actually the Thermal Power Library, or TPL. I will continue to talk a little bit about key features and capabilities, and after that I will show you some examples to make sure that you know what you can actually do with a library. And after I just had the 3 slides about examples, we will take a look at the library contents, and after that I will demo a little bit in Dymola. So feel free to answer me any questions if you want to do that. Okay, so what is Thermal Power Library? It's a modelical library for thermal power systems. So it's a library that can be used for design and commissioning of thermal power plants, and that's include the steam and combined cycle power plants. You can use the library for commissioning, testing of new control strategies, and we also use the library in several consultants projects for development and verification of new plant designs. Other things you can do with the library is controller tuning, for example, for optimal performance, and of course analysis of plant dynamics. Key features of the library there are a lot of different components, so it's a wide range of components, different heat transfer correlations, for example for condensation, evaporations, and there are several different media models that a user can choose to use. The library and the components are quite flexible, which means that you can use several different options, use several different correlations. In many components you can choose if you want to use a static model or if you want to use a dynamic model, and so on. The library is well suited for control design and maybe validation of the control design. It's compatible with the electric power library. An example of what you could do is, for example, islanding, operation, validation, and controls development. So in the library it contains one generator model, but if you want to model more the electric grid, then you can combine it with the electric power library to model that. So a little bit about key capabilities. The library covers the complete steam cycle, so it includes turbines, condensers, boiler, pumps, etc. And it also has a lot of components on the flue gas side, but it do not cover the complete flue gas side. For example, it doesn't have any gas turbine. And we have used it as an important part or customer specific solutions for efficiency improvements and for development of different energy solutions. And a list of applications of what you can do. You can use, for example, for combined cycle power plants, and there's an example of that to the right. We have used it for modeling coal-fired power plants, for investigating and modeling industrial boilers to different industries, for example paper or chemistry. And it's also possible to use it for nuclear, but the library does not include the neutron dynamics. But it's possible to use it for modeling nuclear, to model the steam and water parts, for example. So a few slides about examples of what you can do. So the first example is a Rankine cycle. So it's a closed steam cycle, and it includes some control. So it has pressure and level control of the drum here.
En cours de connexion à la conférence.
And and so in this example, you see that the blue components in the thermal power library, the blue components are steam and water components. So in this example here we have a drum that is heated up under. There's a flow circulating under this drum. And then we have some standard valve components. We have a turbine that is connected to a generator, and also a condenser and a pump. So this example just demonstrates it's possible to model a closed Rankine cycle. And if we continue with another example of what you can do with the library. So this is something that we have done in a consultants project. So we have modeled to the right. It's a model of a coal-fired power plant that it's connected to a CO2 separation process. So we have integrated this thermal power library with a carbon capture library. So this use case is based on thermal power library and the CO2 separation library that we have here. So this is an example of what you can do. So this is a quite large and complex model, and it's possible to model and simulate these types of processes. So the left picture of a screenshot is from the capture plant. Is from the carbon capture library, which is not included in the thermal power library, but it's possible to combine them. A little bit about library contents. The model or the library contains a lot of different models. There's a package called two-phase. It contains components on the water and steam side. So in there you find typical process components like pipes, valves, volumes, and a little bit more special components like separators, steam turbines, boilers, etc. There's another package called flue gas that's for flue gas components. They also contain typical process components like pipes, valves, volume. But it also has some special flue gas components like combustors, fans, etc. There's a third package called solid fuel, third components package. In there you can find the models of coal gas combustors, so it's possible to model combustions. And other type of components that you can find in the library are several different heat exchangers, condensers, several different heat transfer correlations that you can use in the heat exchangers. There's also electrical package that contains one generator model. And there's also a media package that contains several different media that a user can use. So the last slide here is a little bit about references. What I can say is that there's a large European power utility company that uses this library, and also a European power station producer. There's a little bit older published paper about the library. It's called Modeling and Dynamic Analysis of CO2 Emission-Free Power Processes in Modelica using the Combiplant library. So actually this thermal power library, even if it's a new library here for Dassault, we have used it before, and then it was called Combiplant. So Combiplant was can be seen as a previous version of thermal power. And this paper was published here at the Modelica Conference 2006. Oh. Okay, so I can demo a little bit in open up Dymola, so you can actually see the library here. So do you all see the Dymola now open?
Very well, thank you.
Okay, good. Okay, so I now open up the thermal power library here. Yeah. So at the top here, there's an information package we can open. It has a little bit of getting started guide that you can take a look at. It says something about connecting principles. It also have under analysis of a dynamic heat exchanger. It has a simple heat exchanger tutorial that the user can use. If we take a look at the package structure here, we have an examples package where we have different examples. We have two larger plant examples where they are found on the plants here. So it's a heat recovery steam generator example and this Rankine cycle that I demoed before. There's also examples of single condenser. It also example of it's possible to connect it to the Modelica fluid library, but you need a special adapter here. So we have
de connexion à la conférence.
So here we use two components from the thermal power library, and we have used this special adapter, and then we can use components from the Modelica fluid. And there are some more examples, for example of a natural circulation boiler, etc. So there are several examples in the library. Under flue gas is where you find all the different flue gas components. So under valves, it contains valves, a little bit of different valves. Under turbo machinery, it's where you will find a fan model. You have sources and sinks, different types of sensor models, resistances models. On the flow channel, it's the dynamic lumped, it's a discretized pipe model, dynamic model. Under combustors, we have a combustor model for gas combustor. If we go to the two-phase, we have a little bit of similar components, but this is for the water and the steam side. What's a little bit special here is that we have a drum model, for example. We have a condenser model. There's, like as in flue gas, there are valves model, volumes model, etc. So there's a open volume model, like a tank model, included here. Under turbo machinery, you will find the compressor model, pumps models, and the steam turbine model that are based on the Stodola law. Under solid fuels is where you can find this coal solid fuel combustor, which is a combustor that you for gas and coal. And there's also example of here how you can use it. So the example show you that you have a feed of air, an airflow, and then you have a coal source, and then you have a combustor, and then you can see the temperature, the lambda values, and so on. The library also includes different controllers and sensors. There's a generator model under electrical here, and there's also example of how you use this generator model, how you can connect it to turbines. There's also a package of heat exchangers, so they are divided if it's a gas or a two-phase heat exchanger. Most of them are geometric based, but we also have those log mean heat exchangers that are quite common in modeling thermal power plants, especially if you're modeling steady state. Under thermal, you will find wall models, different heat transfer correlations, and so on. There's also a package called visualizers, where you find different visualizers that you can use when you simulate to have a better overview over the result. In the media package, you will find different media models. They are divided in sub-packages called gases, solid fuels, and two-phase. The only two-phase media that you can use right now is this water, and it's based on this IF97. But we plan to extend the two-phase models with some new in a future releases. So I can show you demo 2 examples of what you can do with the library here. So we can start with the Rankine cycle. You will find it under examples, plans, Rankine cycle. And under all examples, there should be some information in the info layer. So if you just click documentation here, there should be information of what the example is doing and what's happening in the example here. So, but I'm just gonna give you a short overview what's happening here. So this is a Rankine cycle. So we have a drum model here. We drag out some water via a pump, and then we actually heat up the water so it boils, and then the vapor will go out at the drum at the top here. It will be heated a little bit more. It will pass a valve, and then it will go through the turbine that is connected to a generator, so we will extract some power from the steam. Then it's connected to a condenser that it's cooled by a cooling flow. So the vapor or steam will condense here, and we will drag it back via a pump here, and it will go back to the drum, and then we have a closed cycle. We have also added a little bit of control to the example, so we want to control the pressure in the drum. So we do that by controlling the valve opening here. If the pressure is too high, we just open the valve a little bit. And we also have a control of the level in the drum, and we control it via the pump here. So if I just simulate this example, it will go really quickly. So I just press simulate. It should only take a couple of seconds. So we can see in the log here that it only took actually to simulate 1000 seconds, it took under 1 second to do the simulation here. So it's a fast example. So I go to the simulation mode now, and I go to the diagram view. As you can see to the right here, we have a visualizer of the pH, so it's pressure on the y-axis and enthalpy on the x-axis. And then we have 4 different points here in the cycle, so you can actually, by dragging this one here, you can actually see what's happening. You can also see that there's several different visualizers in the library, and this is the legend to this visualizer. So it's pressure in bar, it's enthalpy, it's temperature in Celsius, and it's mass flow in kilo per second. And of course it's possible to plot variables also if you want to do that. Most of the components in the thermal power library have summary records, so you can only filter for some. So for example, we can go to the for example, a turbine. We can go to the summary variables here. We can plot the mass flow, etc. And at point 500, you see there's a really something is happening here at 500 seconds, and that's because if we go back to the model, we add extra heat here at 500 seconds. So that's why you see it will then produce more steam, and then the turbine will have a mass flow through the turbine. If you want to plot the power, we can just search for generator, and we can plot the power here. So here you can also see that after 500 seconds there will be more power will be produced. We can also take a look at a little bit about parameter dialogues. I think they are quite standard. So for a valve, you specify the medium. You can specify what kind of data that you want to use for a valve. If you want to use, in this case, an operating point, or maybe you have a kV value from a valve producer that you can use instead. For the condenser, you also specify the medium, the cooling medium. You specify the heat transfer coefficient. You can choose different heat transfer models. You specify the geometry of the cooling tubes here. So you specify how many tubes you have, the length and the size of the tubes. I can demo another example. Is this HRSG, so heat recovery steam generator. I can start. This takes a little bit longer to simulate, just approximately a little bit over 30 seconds. So I start to just set it to 300 seconds. I start to simulate. So I can explain what it does during the time it simulates. So a heat recovery steam generator is something that you can use, but when you want to recover some heat, for example, after a gas turbine. So this is symbolized. It's a mass flow source for gas, so it comes with a quite high temperature. Just you can imagine that the gas turbine have been in front here. And then you want to use the energy in that gas flow. So you feed them through three different heat exchangers, and the heat here it generates enough heat to vaporize some water, so it becomes steam. And after it goes here, you can, for example, connect it to a steam turbine and generate some power. We can take a look at the geometry dialog here. So you specify, this is for a gas water heat exchanger. You specify the medium. You can also specify, because it's a dynamic model, which means it's discretized, you can specify the number of fluid volume, both from the gas side and the water or steam side. It has a geometry record here. where you can specify the dimensions and the number of tubes, etc., of the heat exchanger. If you click here on secondary, which is the steam side, you can choose heat transfer correlations. You can choose between quite many. You can also go to pressure drop here, and then you can choose different pressure drop correlations. And because it's a dynamic model, you also have to specify some initial values. And as I said in the slides in the beginning, there are quite many options that you can use. So for example, you can choose if you want to have static gas balances or not. And in this case we have it true here. Okay, so this is gas coming through the heat exchangers. We have water here that we feed into it. It's heated up here by the gas, goes to drums, and here we take out some water here. We boil it actually. We take out some vapor, goes out at the top of the drum, and then it passes the last or the first heat exchanger, so the steam gets superheated, and then it goes to sink, but you can also pass it to for example a steam turbine, and then connect it to a generator. So what happens here is that at time 200 seconds we increase the mass flow, so it's more energy than in the total energy in the gas flow, which means that we can produce more steam. So for example, if we plot the mass flow from the steam valve here, we can take the summary records here, and then you can actually see just after 200 seconds when we increase the gas flow, then that we produce more steam here. Okay, so I think that was everything that I had planned to show you. So just a quick overview of what you can do.
ミーティングに参加します。
So do you have any questions? So there are no questions about the library or what you can do or anything?
Leo Gall here, hello.
Hello.
I have one question about the solid fuels package. I looked into it and there's only one combustor which looked a little different from the one you had on the application example where you had the CO2 capture plant. So the real solid fuel furnace isn't included in the library.
No, so there's no furnace model. It's only a small combustor. So the screenshot from the CO2 capture example, then we have used this library as a base library to build a furnace. But actually there are no complete furnace model now available. But you can build it from scratch, so to speak. So that's what we did. So we build it by setting up furnace model, different heat exchanger, etc.
Right. The next question are the radiative heat transfer heat exchangers. Are the Hersig heat exchangers, do they include radiative heat transfer?
Yeah, we have under thermal here. It should be under heat thermal, and you go to heat transfer package. No, wait, you should go to. There should be a heat transfer radiation model. Yes.
Okay.
I just don't find it. I think it's
so
under
for the pipe bundles.
Yeah. So if you go to subcomponents, heat transfer, and then we have radiative. So there we have, for example, heat exchanger models for radiative heat transfer. Yeah.
Thanks. I can look into that. Thanks.
Yeah.
And the IF97 water, is it the same model like in the Modelica Media, or is it a different version?
it's not exactly the same. So what we have done is to port it, because we use a different media structure that we use from the Modelon base library here. So what we've done is just ported the code to this Modelon media, because we have a different media structure than the Modelica standard library. But it's the same. We have compared them and so on, so it should be the same.
So that's why we can couple to the Modelica fluid examples, and we shouldn't have numerical problems there, because it's basically the same media values.
Yeah. So I had an example of when you can connect to the Modelica fluid library.
Yeah, there's this adapter in there.
Yeah.
Yeah.
And but then you have to use different media models. But you have to make sure that they are compatible then. But it's only show to that it's possible if you want to do that.
Okay.
Yeah.
All right then. If there are no additional questions.
I have one, if
Okay.
possible. It's Alex from Claytex. I just wanted to know if you could highlight what the improvements you see using your version of media models over Modelica media models. So what sort of improvements in simulation performance or accuracy and so on do you actually get with your modified media models?
I can say that the main reason why we choose to do a new media structure is that we want to use, this thermal power library is based on the Modelon base library, so we want to have one common library with the same structure. When it comes to performance and so on, I don't think there's, with our new water media model, it should be possible to get analytic Jacobians, which is not the case if you use Modelica standard library. So this means that if you have a larger power plants model, you should have some performance gain when it comes to simulation times, etc. But I'm not sure. We've just done a small test, and it's I don't know how much you gain, but it should be some improvement if compared to the Modelica standard library. Otherwise, I think they are quite similar. So it's more about that we use a different structure that we think it's easier to understand and so on in the Modelica in our Modelon media library.
Okay.
Yeah.
Thanks.